And we will turn the initial panel, over to the moderator, Dr. Martin Elvis.
A bit worrying when our people who want to go to space and do all these good things can't get the PC working, but never mind. I'm Martin Elvis. I'm an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, which I'm not representing here. But I'm a total academic, so I think that's maybe why Steve chose me, because I have no conflict of interest with any of what these guys are doing. And it's really great to have with us people who are really trying to get to space in a whole new way. We have the two CEOs of the two asteroid mining companies here. So directly on my left is Chris Lewicki. He's President and CEO of, Chief Engineer, Chief Asteroid Miner of Planetary Resources. Yes?
Good morning.
He used to do a lot of off-road driving, way off-road. He was driving on Mars, but he gave that up for better things. And then to his left is David Gump, who is the CEO of Deep Space Industries, who is the founder of many space enterprises, and this is latest, so let's welcome him too. They're each going to give about 10-15 minutes worth of talking to us, and they each have slides, so we better get that set up. And then after that, there'll be a question and answer session. So when we get to that, you line up with the microphone, and I'll work on that. Thanks. Chris Lewicki.
All right. Good morning, everyone. I'm Chris. Happy to be at another ISDC. Trying to remember when my first one of these are, but it's an annual Mecca. And now space is becoming such a popular topic that we've got two space conferences on one weekend with those who are going to Space Fest in Tucson over the weekend. So in this panel, there's a lot of asteroid topics that are on the agenda today, throughout the day, talking about the opportunity, the business prospects, the ISRU aspects of it, and then of course details of companies' plans and things like that. This morning what we'll talk about, that screen seems okay, that one seems a little bit wigged out, so I assume that's not my problem. This morning the topic is asteroid prospects, and I took that as an interpretation to talk about what I think are some of the most fascinating destinations in the solar system. From a scientific standpoint, from the physics that are present on them, from how much we have learned about these objects, which we only knew existed for about 200 years, and we've really only known in detail for just a little bit more than a decade. So this is an animation. I'll look at the screen that doesn't flicker, and it starts out, it's about 15 years ago. In the center we have the sun, little blue spot on the top is the Earth, to the left is Jupiter, and we'll start the animation. 15 years ago, we knew of about 33,000 objects in the solar system, mostly asteroids. You can see, of course, the main belt between Mars and Jupiter, where the vast majority of these objects are. If you follow the Earth around, you can see kind of a pulsing flash that goes with the phases of the moon, and every time that happens, there's new asteroids added into the population. And what we get, essentially, is you see many more that have been discovered over the course of the past 15 years, and arriving at present day, we're over 600,000 objects total in the solar system, with about 10,000 of these relatively near the Earth. And as you saw during the animation, many of these are crossing our path, and some of them are running right into us. But there's just been an explosion of information about this thanks to the work that's been done by NASA, private scientists, other government agencies, and really people around the world. And from a statistical standpoint, we've only just begun. There are probably about 60 million of these objects that are estimated to exist, down to the sizes that we've been tracking and monitoring so far. And of the really large ones, if you include the main belt, about 1.5 million. We've found most of those. The dinosaur killers of 65 million years past are mostly things that we don't need to worry about anymore. There might be just a couple more somewhere. Of the ones that start to be on the edge of economic interest, the NEOWISE program has refined the estimate of objects in the solar system at around 20,000, and we've been making pretty good progress on those objects, picking up about 20% of them. And I think what Dave and Deep Space Industries and ourselves see is the opportunity, which is made by the last point, that these are in fact the most accessible destinations in the solar system outside of Earth orbit, and even including the moon. And about 15% or more of these objects within the near-Earth object population are actually more accessible than a soft landing on the moon. So we know so much about these objects because we have been pelted with them since the beginning of time. We have about another catalog of 10,000 by definition, near-Earth asteroids that exist in the form of meteorites. And of course, we have studied these in great details in analytical laboratories. That's led to combining that with astronomical observations and doing the good work of science in developing theories and proving those theories through observation. One interesting thing that was confirmed very recently, the large blackish rocky guy on the bottom is a HED meteorite. And we now know with all scientific certainty that we usually know things, that particular object originated from Vesta. And these are things that every day there's something new coming out of them. There has been a very active exploration program in about the past decade, both from NASA, JAXA, and ESA, in exploring not only asteroids, but small bodies in the solar system. Comets and asteroids in many ways have similar origins, but different locations in life and maybe are at different timelines in their evolved lifetime. And of course, it's something that's several $100 million a year have been invested in government programs for doing this work. And that's led to really a characterization of a large variety of these objects. In the first animation, all of the things were really just points of light in the sky. And since 1991, these have become places that we've become more familiar with. Pictures that we can see when we flew by 951 Gaspro with Galileo on its way to Jupiter. And on to larger objects like 20 Lutetitia, and I can't even put Vesta on this chart because the scale of it would literally be off the charts. And those of you who've seen the presentation before know that it's useful to have an appropriate size representation. So this is the Death Star 2, about 77 kilometers, which really helps you give a good scale of reference for how big this stuff is. So if you look in between Eros and Lutetitia there's a little probably individual pixel that's barely lit, and that's 25143 Itokawa. And this is a mission that we have been the benefit of the Japanese Space Agency. The Hayabusa mission 5 or 6 years ago went to this asteroid, touched down on the surface not once but twice, and actually, despite all odds and a number of complications in the mission, was able to retrieve some very small amounts of sample. And when I look at this through the eyes of an asteroid miner and look at this object, the smallest object that we've visited in the solar system, it's really just fascinating. Here is something that before we visited, we thought, well, it's so small it can't possibly have regolith on it because the gravity and the impacts that happen won't hold that material onto the surface. But of course you can see there is plenty of stuff going on there. There's large rocky-sized boulders hanging off the edge that you could potentially go and retrieve whole. If you didn't want to invest in technology to crush and process rocky material in the asteroid. In this case, Mother Nature has done some of that for you in the open seas of the very fine regoliths that have been grain sorted already before you arrive. And we've been able to connect this particular object to the meteorite database as an LL chondrite in terms of its spectral properties. But the real challenge here is there's so much more that we still need to learn about these objects before we can do detailed mine planning and understand how it is that you develop something. So from the perspective of understanding near-Earth objects, it's not something that we are interested in only from an asteroid miner's perspective. There, of course, has been the original interest was for science, and there are a number of items that are of interest for characterizing what these objects represent in terms of our understanding of the formation of the solar system. And this is where you can get to very detailed studies. From an exploration standpoint, for human destinations, they afford a number of advantages on the way to and in the overall ecosystem of human exploration and permanent presence in space. Planetary defense, for those of you who are familiar with the term, is the ability to both detect, characterize, and understand the properties of asteroids so that we can make sure that these objects don't interact with the Earth, as happened in February 15th in Chelyabinsk. And then for all of us on the panel, of course, the resource and the industry's prospect of this is something that there are a number of things that we're interested in going. So what's common really to all of these is a lot of very basic properties, which are not complex to measure. We don't need to find the isotopic ratio of different elements with respect to each other to understand whether the solar system is 30 million years older or younger. That's really a level of detail that an exploration mission from a private company doesn't need to answer. We merely need to understand whether there are 5% volatiles, 1% volatiles, 20% volatiles. And if you look at an object like Itokawa, how uniformly they are distributed throughout the object. So this is something, and our moderator, Dr. Elvis, has written on this, in that while we are going out and commercially exploring the solar system, we are in fact enabling a deeper exploration for all of these other topics along the way, and getting a richer database of information on all these. Planetary Resources has been pursuing this and developing the ARCID series of spacecraft. We will be actually launching into space next year a portion of this spacecraft. You can see me with a full-scale prototype model on the bottom. We're taking the avionics package out of the black area at the end and deploying that in a CubeSat about 10 months from today as a first test of the technology. In about 2 years' time, we'll be deploying several of these in low Earth orbit, and both using them as a technology testbed for our deep space exploration missions, as well as a platform to do remote sensing and down selection on targets that may be of commercial interest. And ultimately, our interest with the ARCID 100 is increasing its capabilities in both communication and propulsion to allow us to take this tiny little guy and get it all the way out to an asteroid with a minimum of expense, and something that we can do with enormous frequency. Just think how many times you jump into the truck and go down to the mine site to check something out or try something out. This is our concept with the ARCID series, is we need access, frequency access, and cost effectiveness of that access to be able to explore this. With the ARCID 100 in orbit, we'll be able to build on the 9833 asteroids that have been discovered near to the Earth so far, and do astrometry, as it's characterized in the lower left-hand corner, of both discovering and refining the orbits of the known asteroid population so that we can navigate accurately to it. We can obtain photometry, which is the process of looking at the amount of light coming in off an object. From that, you can characterize its spin rate. You can start to get some indication of the physical properties of the asteroid from that. And perhaps the best technique, once you know where things are, is to know what it is. And to be able to know from the meteorite standpoint whether something is stony, metallic, or carbonaceous is something that we actually only know for about 5% of the total asteroid population. So while there are hundreds of thousands of targets out there, there is a tremendous amount that needs to be learned in order for us to be able to develop them commercially. And space is a great place to be doing that, because while we do have a lot of telescopes and other assets here on planet Earth that are watching the skies every night, they only can do so, of course, during the nighttime. They have trouble doing it during monsoon season and during full moons, and of course there's maintenance. And from space, we'll be able to do that 24 hours a day, and we will be able to look into the interior of the solar system for asteroids like the Atira class, which cannot be seen quite literally in broad daylight. So we've got a list of targets that we're interested in, represented essentially, in our first interest is in accessibility and doing a general survey of the population. And if you take one of these objects, 2011 UW-158, it just rolls right off the tongue. I know someone's probably writing it down to name their daughter after that right now. This is a run-of-the-mill average asteroid that's out there. We're not certain of its spectral class. We're not even quite certain of its size, depending on its albedo and reflectivity. We do know that it has an opportunity to be visited on the order of every 2 years, and if you're doing a standard Hohmann transfer, it's about 3/4 of a year to get there. And when you talk in the mining community, this is something, the mass of material that's on this object, and depending on what that material may be, the in situ value of it compared to material here on Earth is literally in the trillions of dollars, whether it's in the structural metals like iron, nickel, and cobalt, in the rarer metals like the platinum group metals, or in the most important resource, as I see it in the early development of the solar system, the volatile resources, and most specifically water. This has enough water for rocket fuel, for developing human economies in space and supporting life and activity, probably for, I don't know, decades to come off of this one object, unless we really get going and have multiple O'Neillian colonies to support. Then we might need to get a few more asteroids. So that's just an intro on really what I see as the task ahead of us, the opportunity that's out there. We know more than we have ever known in our civilization about these objects, and we're really taking the next steps to be able to characterize them as a specific resource opportunity. And that is an important part of the overall mining and resource prospect, which makes it just like the mining economy here on Earth. So look forward to your questions in the panel discussion.
Well, we have to set up the other computer, so if anyone has an urgent question, no need to be shy. Pity he missed my talk yesterday, all about how difficult it was to characterize asteroids.
Ah, it is difficult.
Oh, yeah. How are we doing? Good?
We have liftoff. Very good. So I'm going to do a brief discussion, not about the company DSI, but as our assignment was to talk about the process of prospecting and retrieving and processing asteroids. As you might know, I used to be a moon guy. And for a moon guy, asteroids kind of look like the blob. It just keeps growing. We're going to hit 10,000 asteroids in near-Earth space by the NewSpace conference in July. And by the time we start launching our first probes out, we'll probably have 12 to 13,000 potential targets. It's a challenge if you're looking at it from a business sense, because one of the things you do in business is to cut down your options to the best ones. And with asteroids, new options keep popping up as they get discovered. We're somewhat different from Planetary Resources in that our first missions we call Fireflies. They will be going out on one-way prospecting trips. They use a CubeSat style architecture. That's a 12-view CubeSat form factor. And this picture is completely fake. I think that's Itokawa, and one of the reasons we're doing Firefly missions is that we don't actually have any images of asteroids smaller than about 500 meters. If one of your goals is to bring back much smaller objects to parking orbits near Earth, you would like to know whether they are like Itokawa and large asteroids as rubble piles, boulder and gravel held together by their own weak gravity, or whether they are, as theory suggests, more likely to be monoliths, solid objects. And that makes a big difference when you're trying to plan a retrieval mission. So we will send out Fireflies on several of these trips to get that very basic data on are they solid, are they rubble piles. If we go to one that we might eventually retrieve, we'll know what really is its volume. Because for the smaller asteroids that are just pinpoints of light, you don't know very much. You don't know mass, you don't know volume, you don't know shape. Many things that you really need to know before you can plan a retrieval mission. So we have basically 3 types of Firefly missions. One is to go to known targets. One's one of the 10,000 that have already been identified. We can go out to a sphere about 4 million kilometers in distance. And what that will do, we'll get data for its next close approach, which, depending upon the target, could be as long as 2 or 3 decades from now. And as I said, it will also start to establish some empirical data points about what smaller asteroids' structure really is. Another type that we have is to go after newly discovered targets that have made a close approach. We chase after them and get both data for the next close approach and potentially refine the trajectory estimate for that close approach so we know better when it will come back and how much danger we might be in at that next close approach. And the final one is to go to a known target anywhere in the near-Earth system. You would use this if you had a particular asteroid you intended to retrieve and at some point in the future, and you had to go out, if you were a sensible mining company, and get some data on it before you launched a very expensive retrieval mission. That is more challenging. You may have to chase halfway around the solar system to be able to get to it and get some data in time for its next, actually much closer approach at some later point. The way we're approaching this is to build and launch 3 in a campaign lasting 2 to 3 to 4 or 5 months. Most space projects incur enormous amounts of expense by trying to bake out every single possible risk and failure mode before they launch. And the space environment is different. You cannot replicate everything about the space environment on the ground. You can get close, but not all the way. And there are certain kinds of errors that just don't get found. You know, there was a Mars landing that crapped out because of a small error in software logic. They were going to listen for the big bump when they touched down and then turn off the engines. And they started listening too soon and felt the bump of the parachutes being released and shut the engines down and crashed after that. And so sometimes you just need to go do it, and if our missions are low enough in cost, it makes more sense to go do it with a 95% chance of success than spending another year in the ground to try to get it to 97% or 98%. And since these are launched on secondaries, we also get the benefit of being able to put them on different launch vehicles, which besides mitigating the potential that one will be lost in a launch mishap, it also means since you're a secondary and have no control over what the primary spacecraft is doing in its schedule, if one gets delayed, as they often do for its own reasons, you've got another launch coming up on a different vehicle that's not been delayed. So then we move on to dragonflies, and one of the reasons that we like dragonflies is because it brings back samples. This is one of the great illustrations that our artist Brian Versteeg has created for us, grabbing a 25 kilogram sample off the surface of an asteroid. It could be, almost any size. No telling how far it extends above and below the frame of this picture. And when we bring that back, we learn very important things. We know for sure what the chemistry, the elemental and molecular makeup of that target is. And it also is very important that we'll learn something about the material properties and have feedstock for pilot processing plants. We sent some meteorites off to a metallurgical firm and asked them to extract the metal from these meteorites and turn it into something useful, a tube or a tool. And they came back to us and said, well, this is hard. We tried grinding your darn meteorite to get it into granular form for processing, and 20% of the mass of the sample was actually the grinding material from the tool we were using, and only 80% was the actual meteorite. So it's really important if you're looking to process that asteroid to know what its properties are. There are some that will be mixtures of volatiles and metal particles, and you may want to go for one with high volatile content even if you're interested in metals, because if they're distributed as grains already, you can skip the whole grinding process and save yourself a lot of energy and time. So it's something that a commercial company would really care about, that a scientist might find interesting, but not quite so central to whether or not they succeed in turning it into something that can be sold to a customer. And obviously we'll have samples to sell to researchers and samples to sell to collectors. Jeff Notkin will have a field day on that one. Now, I guess I'm less happy about the state of our knowledge of asteroids than Chris is. Primarily, I'm haunted by the mass uncertainty issue, especially for the smaller targets that you might want to move back to Earth orbit. The brightness does not really tell you what its volume is and doesn't tell you what the mass is. That's because asteroids are not in a nice bell curve distribution of density. They are a bimodal distribution, and at the average, there are very few asteroids that have average albedo. And so if you say, we found a bright point of light of a specific brightness, if we apply average albedo to that, we will be almost 95% sure that we are wrong. That either it's much darker and much bigger, or much brighter and much smaller, but certainly not the value that we've applied to it. This is illustrated by one of the asteroids that we use as a as a straw man example for retrieval missions, which is 2001 GP2. I've learned how to say that very quickly, Chris, just as you have on others. And as you can see, if it's a very bright nickel iron metallic fragment, it may have 1,400 tons mass. If it's a very dark comet core or carbonaceous, it could be 20,000 tons of mass, assuming a perfect sphere, which of course it probably won't be. So the uncertainty in what you're going to retrieve has to be retired in some fashion. Otherwise, you have a great risk that your retrieval mission just will not work. So we see the three basic kinds of asteroid retrieval missions. One is the now classic Keck approach: go find a small one, bring it back. Because it's small, unless you've done a precursor mission, you really have no idea what its structure, shape, volume, mass is. And if you're in flight trying to acquire that target, because it's small, it's going to be a challenge to actually get it acquired as you're in flight. Another approach to it is to just pluck material from a larger target. These may be ones that have been characterized already for at least what they appear to be from their surface reflections. But if you're going and gathering material for your basket, it overcomes the mass uncertainty. You just gather until you reach the design mass of your return mission, and you're finished. But you're limited to surface materials, which may not be representative of the asteroid as a whole, and may not have the enhanced volatiles that you are hoping for. And then the third approach that we've thought about is to go take a portion, be able to take a portion of a target. It's probably not PC, but you could bring some explosive device and crack a portion off and bring back the piece that fits your goals for the right mass. Pretty technically difficult. And so when we look at these three missions and analyze the risk involved, whether in terms of, do you do a precursor, do you do just a flyby precursor, or do you go there, rendezvous, or bring a sample back? And without a precursor, fetching a small asteroid back, to our analysis, is simply red. It's folly to attempt to do that. If you do a flyby, you'll get its volume and shape, so at least it won't be the wrong shape or the wrong volume to fit your collector, but you still won't know much about the mass. If you do a sample return, you'll know the mass, you'll be able physically to bring it back. The collecting of boulders and gravel, you could do that without a precursor if you were sporty. You wouldn't know mass until you got the sample return, and the shattering it or slicing it to our minds is sort of a yellow across the board. Until you actually attempt to do the shattering, you don't know if your approach to that's going to work. So that's how we have begun approaching the analysis of how to do asteroid prospecting and mining, and I think we can now transition to the Q&A sessions.
Right, thank you very much. So do come up to the microphone and ask questions. Oh, we have one already. Okay, please.
I have a question. My name is LaJolla. I'm an aerospace engineer, and my question is, how well do you know the mass of an asteroid? Because let's say for the mass of the Earth, you kind of know the mass of the Earth because of the Moon. It's a two-body system. Well, if you have an asteroid, could you send a flyby mission, and with the mass of the satellite and the influence of the asteroid, can you find more information about its density with that asteroid?
Who wants to answer first?
Well, for a flyby mission, no, you don't learn mass, and that's the great issue with just doing a flyby.
Unless it's a very massive asteroid.
Right, which you may or may not want to take the risk of
Yeah.
aiming back at Earth. But you get the volume, you get shape, but you have to do something beyond a flyby to get mass.
Yeah, and this is, as David was describing, it's one of the big challenges in that it starts, at first you have optical properties. You have to make an assumption about albedo, and then you have an uncertainty in your ability to determine absolute magnitude that you've been able to observe it. And then, of course, the thing is spinning, which puts a little bit of some sort of bounds on it. The ones from a remote sensing standpoint that we get the best estimates of mass from are those that come close enough to the Earth that they become a radar target. So Goldstone or Arecibo are both able to put a better condition on their surface properties in terms of radar albedo, which helps bound optical albedo. The NEOWISE mission is able to use it, and when it was a prime mission, it's 4 different IR bands to get a very good constraint on size, but you still have to make some assumptions about albedo. So this is really the big challenge when you want to consider moving it around or trying to do an economic analysis about how much material may be there. And it's for the ones like Vesta or Ceres or probably Eros is just about large enough that you can see the influence of its gravitation on your spacecraft. But Itokawa is too small for you to even be able to notice that. So.
Second question?
One more answer. Like the Keck study, for example, there's another thing too where to determine the mass of the asteroid, you can push it. But of course, you have to already be there and be fully committed by that point before you do that.
Could you let the other lady have a go and join the back of the line again? That's right. It's more fair that way, I think.
First, I'd like to thank Chris at Planetary Resources for the great public outreach campaign you've done, keeping everybody informed of your progress through the emails and through the PR campaign to capture the public's imagination.
Thank you.
I think that does a tremendous amount towards furthering all of our interests in space. Mm-hmm. And second, my question is, how are you collaborating with the U.S. government or other governments around the world in your quest to find and characterize asteroids to help keep the Earth safe?
To keep the Earth safe, okay.
Yes. And have you considered purchasing any of the telescopes that are for sale, because we can't seem to fund science and stuff?
Yeah, so a couple different questions in there. It goes without saying that the businesses that we're talking about today wouldn't be possible without the 50 years of space exploration that preceded them. And there's a lot of great work that continues across the board in terms of detection, characterization. Groups like the B612 Foundation that are promoting awareness and activity at an international level for topics related to planetary defense and security of the Earth. We've been certainly in a lot of active conversations and collaborations with NASA and other industries. The Minor Planet Center has been very cooperative with topics on us. We'll be announcing a project soon related to doing some work in existing asteroid data and improving our knowledge of it. To answer your question about all these assets that have been coming up, there's probably 2 that I would point out in particular. One would be these mysterious set of optics that have been gifted to NASA by, I believe, the National Reconnaissance Office. And then the second is telescopes like Siding Springs in Australia, which indirectly received some NASA funding. And in many ways, I mean, these are good things to be funded, but they're things that are kind of funded at a government scale. And from a private business standpoint, it may not be the most cost-efficient way for us to achieve our objectives. As an example, these telescopes that the NRO has been made available, they can only be put in space by a launch vehicle today that costs $250 million. So there are ways to get a good fraction of the benefit of those missions with only a small fraction of the invested cost. But this is something that we were just talking about this at breakfast this morning. That a lot of work and interest in asteroids continues all around, and there are ways for us to collaborate in doing that. And we spend a lot of our time finding those ways.
And a little advertisement, if you guys can stick around, I'm going to be talking about what you could do with those spare telescopes. Right next. Carry on.
No, I think we're both obligated on.
Now you know to skip town, right? Okay.
My second question is, to process the ores on the asteroid. I think Chris, you mentioned about like having a magnifying glass or something like to use solar power to bake the asteroid. Can you kind of further explain what the idea was?
Yeah, well, so that's in particular to volatiles on asteroids and water. It can be thought of conceptually as simple as a distillation process, much like you purify seawater. And a great benefit of any operation in space is you have two resources available for free in vast abundance. You have this wonderful ball of fusion at the center of the solar system, which has got a pretty good warranty on it still. And then you have most of the rest of the sky, which is at 3 degrees Kelvin. So from an industrial process, you have an energy source available from a thermal standpoint, and if you want to go photovoltaic with that, you can. And then you have a cold sink. So in the process, for example, of obtaining volatiles from an asteroid, you can do something as simple as heat it up, capture the vapors, and then use the cold sky temperature to condense those vapors out in a particular spot. And there are even ways to extend that into processes that address the metallic resources on asteroids as well, although those get a bit more complicated than distillation.
But what about hydrogen? Like hydrogen is like the hardest one to contain. How would you contain hydrogen?
Well, that would be processing the water essentially that you to recover. So you are collecting H2O. And it's our opinion that you would probably keep your hydrogen stored along with an oxygen atom for transport, and then when you want the hydrogen, separate the two.
Thank you.
My name is Robert Gideon, and my question is for both teams. I see there are two companies here today, DSI and Planetary. So do you imagine that this industry is competitive? Are you even in competition? Do you think of that way, that you are in competition with each other?
Was the question, are we in competition with each other?
Yes, DSI and Planetary. Do you see it that way?
I think in some ways, yes. In many ways, no. Do you agree with that assessment?
Yeah, it's a Venn diagram. You know, we have similar but not completely identical interests, and we have certainly different strategies for how to go about achieving our goals. And it is very useful to have at least two companies going in to see customers, to see other parts of the supply chain that we might want to serve. Intel, for example, would sometimes help competitors into business because Intel's customers didn't want to have a single supplier. They demanded a multiple set of suppliers. So in that way, we're helpful to each other.
Yeah, I'm actually very excited, not only for just considering companies who have asteroids as a focus, but every aspect of a business-based operation in outer space in many ways benefits the entire community. David and I could create the two world's most successful asteroid mining companies. And if there is no one who is interested in the resources, it will not be an entire economy. So we need companies interested who are developing fuel depots, companies who are interested in doing structures in space on space-based resources, companies who may be interested in having the moon as a focus and building up capability on the moon, and of course everything between here and Mars. And what we're really talking about is an economy that has all of these things together, and usually an indication when you have multiple people pursuing a goal is a good sign. So thank you.
Good morning. My name is Doug. I'm a physician from Southern California here. Chris, you mentioned in sort of your introductory comments that in terms of the discovery of, like one kilometer or more asteroids, that there's a few still out there, but we've mostly discovered them. So a question for all of you guys here. Do you guys think that we are, to a large degree, humanity is not threatened with extinction from asteroids?
I don't know if I've thought about that so specifically. I do think we're still threatened by extinction. Maybe not in the same way that the Cretaceous-Tertiary boundary and the Chicxulub crater impact presented. But something just, one order of magnitude larger than the bolide, 17-meter bolide that hit Chelyabinsk, hitting a population center or any place on the Earth can, there's lots of discussion about climate change. An object like that interacting with the Earth and distributing material has a global effect and will have a very measurable effect on the climate. So it, up to a point, doesn't take a multi-kilometer asteroid to create that problem. And I think it's extremely important that we not rest and we keep getting these objects probably all the way down to, sub 100 meters and knowing exactly where they all are.
So it could ruin our economy, but is it really an extinction risk? Is something 50 meters or 200 meters, or it's not? So
Well, nothing's an extinction event if we're all not living on the Earth.
hey, I'll second that motion.
Good to have a backup plan. Okay.
Okay, thanks.
Yeah.
Hi, I'm Michael. I was really excited by the relatively recent launch of both of your companies, and I just wanted to ask, when do you expect to start to be profitable?
Sure. So this, I think, since I would call it the dot-com crash, was a good milestone in all of our histories of recognizing the combination of the passion that we all have for space and pursuing opportunities in space. And I think many of the companies that have been formed in space-related topics since then have had a very specific and shrewd business approach to this. It's not just about the dream. It is about creating a viable business which creates value for a lot of people. And our strategy at Planetary Resources has been our mission and vision of expanding the economic sphere of humanity off the planet through the use of asteroid resources. And in doing that, we're doing much like the original space race did in creating derivative technologies and benefits of things that are useful to people who don't even consider space in their daily lifetimes. And nearer to our mission and vision, there's a lot of useful innovation that's going on in our company and elsewhere to create things that are useful for NASA, for other parts of the government, and for industry. And we've been successful in identifying pieces of our roadmap and investing our own money and combining that with money that's available in the form of research grants and things like that, to where we both benefit from that as well as the grant source of benefit for that. So, we've been able to make a profit since our announcement, and it's tough. I will say it's not an easy thing to do, but it's something that we think it's very necessary to have a business proposition that goes all the way out to the point of recovering material from an asteroid.
Thank you.
Hello, my name's Ed. I had a question for both of you. At this point in time, I don't believe we've actually managed, I remember reading about an experiment where they were attempting to even weld in zero-G. I don't know if anyone's attempted to smelt in zero-G. I was wondering if you've started exploring that idea.
Well, we have a project we call the Microgravity Foundry, where we are able to extract nickel from a nickel-iron asteroid using a process that is indifferent to whether there is a gravity field or not, and then using a 3D laser printing process to cause that nickel to assemble into a fabricated object. So I think in space we'll all be looking more at the additive manufacturing approach to working in space, and not the big Detroit foundries and smelters that are stamping out gigantic pieces. Another great thing about doing this in space is with microgravity and vacuum, you can do a lot of manipulation down to a molecular, almost atomic scale, and perhaps create things that just simply can't be produced on Earth.
In a gravity well.
Yeah, exactly. In vacuum, in addition to the great fusion supply, there also is free vacuum. That is, expensive to create on Earth, and you can create metals, for example, that if you don't want them exposed to oxygen, it's easy not to expose them to oxygen, which is very hard on Earth to pull off. And because it's microgravity or zero gravity, alloys that on Earth you couldn't do because they have different densities will in fact stay mixed in space, and you could be able to create alloys with properties that it's hard to envision now until you actually are able to do that in space. So I think we're going to keep a lot of engineers very happy for a long time.
Yeah, I think a lot of times, especially when you're thinking about the entire opportunity for resources in the entire solar system, it's easy to imagine activities on the moon because we're very familiar with the environment of gravity, even if it's 1/6 gravity. And that's a challenge that's often put out in developing asteroidal materials because, well, there is no gravity. Isn't that going to be hard? You need centrifuges. And I think we see actually a lot of opportunity. It's not intuitive. That doesn't mean that it's hard. It's just thinking about it, and it presents many more opportunities, like, for example, being able to have magnetic or electrostatic forces that don't have to fight with gravity when you're talking about influencing minerals, molecules, or atoms. So there are a variety of things that you can do that you couldn't do anywhere else in space. And actually, I think the most challenging thing is being able to get to that environment and being able to iterate and experiment in that. So I'm looking to having spacecraft and test beds in space to do that, to having more space stations, commercial astronauts available to help in laboratories and microgravity to explore these things.
Yeah, I just would add a point there. To date, a great number of the people who have actually flown and experienced space have been test pilots. Then there have been some scientists added, very few engineers. I just can't wait till there have been hundreds of engineers in space actually experiencing it firsthand, because we are descended from monkeys. We do expect gravity. It is so built into how we view the universe. And having engineers experiencing the space environment and then thinking about, well, this could be a feature, not a bug. I think we'll have a lot of developments that are hard to envision now.
Excellent. So one last question, I guess.
Yeah, so mine is actually an engineering question. I think it's fun and interesting to talk about the business case and talk about the actual mining operations. But I'm wondering, in the short term, both of your companies have these prospecting missions. What is the tall tent poles from a technical point of view and from a cost point of view in order to make those sort of surveying spacecraft affordable? Is it the propulsion? Is it the proxops? Is it the take your pick? I know it's easy to say all of those, but what are you struggling with?
Well, I don't know if I would describe them necessarily as tall tent poles. In fact, a lot of this stuff is very achievable. Technology exists for doing this stuff today. Technology in many ways is not the challenge. In the problems that you're overcoming, and you're hitting them, propulsion in delta V is ever present. The price of launch has gone up in the last 50 years, not down. It may eventually come down, but the physics are still there in that you've got mass fractions to deal with. After you are operating efficiently with the propulsion to get out to objects millions of kilometers away or hundreds of millions of kilometers away, you then have the inverse square law at the bay in communications. And this is a problem that NASA had originally solved with very, very large dishes and very expensive assets. And we're looking into optical communications for a variety of reasons that reduces the overall size, weight, and power and is a lot more feed forward than RF technology has been. After that, I think it just goes to being able to continue to make progress at a rate where you can iterate, learn, and move things forward. And that's why our company exists. Is that the time is right, the capability is there, the funds are available, it's within reach, and that's why we're pursuing it.
As Chris said, it's really not technology that is the challenge, it's the technology that you can afford in the business plan. We are basing most of our work on CubeSat style technology, so you can buy a kit from over the net. That's not the problem. As Chris said, communications is a challenge. We're going to probably stick with RF for a little bit because we've heard horror stories from people who have developed laser comm. But that puts us in a bind because in addition to the technical issues of establishing that link, now you're fighting with billions of cell phone users and others across the planet who have filled up the spectrum. As I understand it, there is no assignment for commercial use of deep space frequencies. That could be what hoses us in rather than a particular technology.
Okay, thank you very much. Let's thank our pioneers in space business here. And we move on to the next section.